get started, I'd just like to tell you guys a story. A few years ago, I was in a data structures and algorithms course at Swarthmore, and we had to implement breadth first search and depth first search for a lab. I didn't have any problem with it then, but then we had to do a study guide for our final exam, and I completely blanked on how to do breadth first search and depth first search, just executing the code on paper. So I had a friend show me an example, and I looked through the pseudocode again, and I was able to sort of store it in my short-term memory, but it didn't actually stick. So the next year, actually, I was in discrete math, and the teacher was writing breadth first search and depth first search, the execution on the board, and I was doing my best to copy everything down, but when it came time to actually show the execution on the homework assignment, I'd forgotten the order of the steps, and by looking at my notes, all I saw was the finished product. I didn't know how it got there. I didn't see the sequence. So all that time that he spent writing it down and all the effort I spent copying was actually, I guess, wasted. So fast forward one semester, I'm in AI, and we learn state space search, which can act as both breadth first search and depth first search based on a single data structure. So I thought, okay, fool me once, shame on you. Fool me twice, shame on me. But breadth first search and depth first search are not going to fool me for a third time. So I decided that I was going to commit this to memory. And what I did was I just kind of rehearsed the pseudocode out loud to myself. And as I was doing this, I was just playing with the rhythm and putting emphasis on different syllables. And I said, this sounds a little bit like music. Maybe I should just make it into a song. And I did. And lo and behold, my teacher, Lisa Meaden, asked, show the order that nodes are visited for breadth first search on the test, and I was prepared. So that brings us to the talk for assessment of introducing algorithms with video lectures in pseudocode rhyme to a melody. I'm Ben Schreiber. Over here is my colleague, John Doherty, professor at Haverford College. So let's talk about the agenda for today. First, we have the motivation behind problem solving. Then we're going to introduce the solution, talk about why it can work. More details on this are in the paper, but we will give an overview. And then how it can work. So we'll talk about a study that we conducted at both Haverford and Swarthmore College. And lastly, we'll talk about how you can implement it in your classroom and ideas that we have for the future. So, what is some of the motivation behind this solution, or the problem we're trying to solve? One thing is that instructors are increasingly overwhelmed with growing CS enrollments, and their faculties might not be growing at the same, or the proportional rate as the enrollment. So there's also a lot of technologies being developed, and additionally to the classes growing, students are of various learning styles. So some people prefer visual explanations, other people prefer I guess more verbal explanations, and rarely a student will have a strict preference for all contexts. So additionally, it's really great having a problem-solving environment in the classroom where students can interact with each other and bounce off ideas and help each other out when they get stuck. However, this can be pretty tough to implement because there's just a lot of curriculum to cover, and also sometimes doing the pre-reading with a lot of text isn't that friendly. So also, as I have experienced, it can be easy to forget the steps of an algorithm. And I mean, this is a story I've heard, but there was once a professor candidate at Swarthmore who wrote incorrect binary search pseudocode on the board. So even somebody who's really versed in the material can make a small but significant mistake. So the overall question that we are trying to answer is, how do we introduce algorithms in the most efficient and effective way possible? So the solution that we propose is a 3-part video series where each video has a unique purpose. The first video is intuition, so just high-level pseudocode, and then we use the pseudocode to narrate through the algorithm step by step over this interactive blackboard. So you can see here that we're using the low and high indices to compute the middle index to show which range of our list that we're searching for a key in binary search. And I'll use binary search as an example here, but this series can be applied to any algorithm. So the second video in the series is analysis. So we introduce the idea of Big O from the ground up to a user who has no prior experience. Then we tell them a simple approach to classifying an algorithm into a Big O family, and we use this approach to apply it to our algorithm of interest. So here, for an algorithm that took 4n squared plus n steps, we drop the constant coefficients in non-dominating terms to evaluate it to O of n squared. So we see that n squared goes faster than n, that little graph. So the third video is the song and code, which takes some of the facts from the analysis and the pseudocode from the first video, bundles it up in a song, and actually uses the song line by line to write the algorithm, in this case in Python. So here's the binary search song.
Binary search looks for a certain key. It plucks the array in until it finds the key. The array must be sorted for it to work properly. But at home all wrong and it keeps searching when you're using recursion or iteration. Bubbles stick to the ladder for our implementation. But it takes low, high, and an array. While low is LEQ, high you should iterate. Find the midpoint between the low and high indices in an array that is greater than the key. Set high equals to mid minus 1, and keep the low position. Else if array then is less than the key, set low to mid plus 1 and let the high just begin. Neither of the if conditions happen met. You found the key, so we turn the mid index. If from the while loop you happen to exit, then nowhere in your range does the key exist.
So, hope you like the song. Here's the actual mapping from pseudocode to equivalent Python. So if we just go line by line, as input it takes low, high, key, and an array. So we define a function, binary search, that takes as parameters low, high, key, and array. While low is LEQ to high, you should iterate. While low is less than or equal to high, you loop. So the rest carries on like this. There's pseudocode in the handouts that JD was passing around, so if you're interested, check it out. So what are the benefits of this solution overall? For one, it assumes very little background knowledge. I've tested this on people ranging from my grandfather at 90 years old, who's very sharp, but doesn't have training in computer science, to high schoolers who have done some coding, to software developers who might not be familiar with Big O, to mathematicians who've never programmed before, and many computer scientists like yourself, and for the majority, computer science students. So it's seen a lot of eyes, and although I feel like I don't have the thickest skin in the world, I am always open to feedback. So if you guys have it, please tell me. So the explanation is also sequentially very natural. It takes you from English pseudocode, execution by hand over this interactive blackboard, introduces the idea of a Big O from the ground up, and then applies it to the algorithm of interest, and then bundles the facts from that video and the pseudocode into a song, which we can use for an implementation. Also, because we're using a multimodal approach, it caters to a lot of different learning styles, and students can also learn at their own pace because the videos allow you to fast forward and rewind, so you don't have to worry about copying the notes there. So Lastly, it's easy and free for teachers to use, and it can save lecture time because you can just assign it before class. So why can this solution work? What is the foundation underneath the solution? So for one, humans do have a unique relationship to music. So there are studies where people with Alzheimer's disease, multiple sclerosis, and various other brain injuries or diseases who have used musical mnemonics as a tool to retrieve verbal information. And what it does is it allows, so these compromised areas of their brain where they used to have information stored no longer function properly, but they're allowed to use the global power of music to retrieve the information elsewhere. So songs also have stood the test of time in transferring information throughout history. So we see that the Iliad and the Odyssey are both written in hexameter rhythm. The Old Testament is written in verse. And also throughout your history, I'm sure you've memorized the ABCs quite well and still know how to sing the national anthem. And lastly, it complements visualizations really well for students who are blind and low vision. So we have three modes: the musical mode, the visual mode, the auditory mode. And for those who might not have the visual mode, they still have two other modes of communication with this material. So we conducted a study as well to evaluate the effectiveness of this solution. We surveyed the videos at two different colleges: Swarthmore College, where I went, and Haverford College, where JD is a member of the faculty. And our primary goals for this study were to evaluate students' technical grasp and how much they had increased in confidence before watching the videos and after. So the sequence goes like this. First, they did answer a pre-survey, then they watched the videos, and then immediately after they were to answer a post-survey. So what goes in the pre and post-survey? First is a question: how confident are you about coding this specific algorithm? The two algorithms we surveyed were selection sort and binary search. So the second question is: how confident are you on the understanding of Big O? And the last was: can you identify the time complexity of the algorithm? So we asked these same questions in the post-survey in addition to two other conceptual questions. And we also asked Likert scale agree-disagree questions. So they were to answer on a 1 to 5 scale, where 1 is strongly disagree, 3 is neutral, 5 is strongly agree. And the last thing they were to answer, which is actually optional, were questions about gender and race, which were all free response. So the survey population. For binaries, first we had 3 different sections of CS1 at Swarthmore, each section taught by a different professor, and we had 2 different courses at Haverford, so both a CS1 and a CS2, and they were both taught by my colleague JD. So the totals are both over 30, which allowed us to employ statistical tests. So here are the first results for technical understanding. We can see that there's a 70% increase in the accuracy of students' responses for both selection sort and binary search. So you can see the green is their pre-test accuracy and the purple is their post-test. So basically this is over a single question. Can you identify the time complexity of binary search or the time complexity of selection sort? And they chose from 6 responses, one of which was I don't know. So there was no guessing here. Also, they answered 2 other conceptual questions. One was an execution, so tell us if the value at the middle position is less than the key we're searching for, what should we do in binary search? Or a more conceptual question, so like, what statement is true about selection sort? So we can see that each one of these questions was answered correctly 80% of the time at least. So now let's look at the confidence questions. So again, it was just how confident are you feeling about the concept of Big O before and after, and how confident are you feeling about coding the algorithm, both in the pre-survey and the post-survey. And we can see that there's a substantial increase for both algorithms. I should say that binary search was previewed first in many of the courses, so that can be why it was slightly higher than the selection score, but both substantial increases. And then we wanted to examine this further by saying, okay, is this biased towards one gender? Did one gender experience a higher increase in confidence than another? Because we did not want to make the videos biased. So we found that there was actually no statistically significant difference between the actual numerical value of how much women increase in confidence versus how much men increase. However, we can see that based on their baseline score, women actually experience a higher percent increase, but again, no statistically significant difference between women and men, how much they increase in confidence. So now for the qualitative statements. So these statements were answered on the 1 to 5 Likert scale. So 3 here is neutral, and let's just take a look at some of the highlights. Students thought that the videos flowed naturally. They seemed to make the information more fun, less intimidating, and it was a good study resource. We also asked negative questions to ensure that the students were actually reading these survey questions, so they weren't giving us all positive feedback. And we can see that they didn't feel like it wasn't helping their understanding, and they didn't feel like they were wasting their time. And just to see if it would work, we wanted to see if students would remember the algorithm better after just a single listen. And actually, although the responses are below neutral, 20% after just one listen felt it would already improve their memory. So, how can this work in your classroom? Well, for starters, you can just assign the videos before class, and I would greatly appreciate that. But if you want to take it a step further, you can assign both the pre and post surveys to your students, which we will provide, and whenever you would like, we will provide you with this data in an Excel spreadsheet so you can do your own analysis. So basically, this will allow you to see, okay, how well are my students understanding the material before class, and how confident are they feeling about it? So, what's in store for the future? Well, we want to experiment with other genres of music. So, exploring pop music, maybe hip hop music, maybe some familiar folk tunes. Also, one thing we really have to do is captioning to make the videos accessible. Another thing is employing a control group in our study. So, what would happen if we just had them read textbooks, and how different would the responses be for these pre and post surveys, or rather post surveys? And then we want to keep developing more series. So, there's a bubble sort coming out very soon. Then there's merge sort, the original depth first search, breadth first song, breadth first search song. And then we want to expand our network at universities and break into the high school and middle school scene. So, what are the takeaways from this presentation? This solution allows students to peek inside the execution of an algorithm at their own pace. They develop intuition by doing this and retain it with rhyme pseudocode framing. And it's also free and saves you time. So I thank you for being here. I thank the study participants for all being
Great, thank you very much. Questions?
I just want to ask if you have any data on learning retention. If, for example, after a week or a month, if they still remember either the song or the algorithm. Do you have any data on that?
No. So it was all in the snapshot of the pre-survey. Immediately watch the videos and then immediately.
Do you have any intuition on how that would work?
On
Because
evaluating.
I don't know if the students would still remember the song after a week. Or
Well, the evidence that we have right now is through history. We just have songs that have lasted forever, and we have poems that have lasted forever by being tied to music. But yes, we could employ study over a longer period of time to actually test whether they're memorizing the information. But really, the primary goal behind this is just for understanding. Memorization would be great, but if you can, memorization of the song rather, but if you understand the material anyway and memorize it without the song, I'm equally as happy.
Do you ever have students write the songs?
I've never,
I mean, with active learning and stuff, it seems like that might even be more engaging for them.
I'm sure that would be a great idea.
Also, thank you for this wonderful upload. I already feel like I have to dance to my students in worries me slightly. But I also, like, I think the control group thing is a very important part of the thing. You mentioned as a possible thing you might do in the future is read a textbook, but I don't think that's necessarily a fair comparison. I think your premise is that the modality of music specifically is useful. And so I think for your control group, you should compare well-produced animated videos which don't have music but have similar dynamic qualities to the music. Because I think part of your argument is that music specifically helps. So I think for the control thing, you need to compare video with video. You can't compare video with text. It would be
That's a very good point, but I'm actually endorsing the whole package. So I don't think the music by itself is a teaching device. It's what bundles up the information, but it won't work without the foundation from the previous two videos. So I'm actually advertising this as the entire package, the multimodal approach.
Yeah, I'm going to make a prediction. I think based on years of research into algorithm visualization, we know that what really matters is how actively engaged people are with this. So the comparison that's going to make the difference is whether, as the gentleman up here suggested, they make up their own song or they sing it themselves.
Yeah.
Just passively watching the video is going to be, you're not going to get as much of a gain based on what we know about past learning research as compared to actively singing the song, making it their own, or even creating their own songs.
Yeah, definitely playing around with the information is
So
really
if we were going
important.
to do a future study, I think that's where I would focus, is on trying to make it more active.
Okay. Thanks for your point.
This man right here.
Are you suggesting karaoke?
Yes, we do that. We do karaoke.
All right, one more question. Yes, sir.
Pushback from
I hear.
students, do they feel this is something that they would have done perhaps when they were in kindergarten or something, or did they
Oh
actually
yeah,
embrace it?
there was one response. I feel like I'm in middle school. I'm a college student. How could I possibly include music in my computer science stuff? But this person answered all the questions correctly. So, I mean, it seemed to have worked for this person.
So you're not getting any negative feedback from the students in terms of they're finding it silly or?
I didn't. Other than that, I didn't find that they were finding it silly. No, but I mean, there was both positive and negative feedback. But here, if we go back to this, we can see that the students overall thought the videos, or on average, thought the videos were more fun, or made the material more fun. They thought that they were sequentially natural. They thought that the lyrics translated well, and they didn't think that it was a waste of time, and they didn't think it was hurting their understanding on average.
Wonderful.
Can I chime in real quick? Just
the
afterwards,
advisor.